know, and you can see, I watched this video. Jesus Christ. After the video of this issue, Andy said, no, that's bad. You should be ashamed of yourself. It was horrible, didn't it?
Okay, everybody needs to double check and make sure they have the correct clicker. Because somebody who wasn't here, like they dropped the class thing, they got points the other day. So what that means to me is somebody took the wrong clicker. So, and I don't have any way of knowing who it was. So, y'all need to just double check that. Okay? Okay. All right, you ready?
Sure.
Hey, it's raining out. It's a good day to stay home and study your
You're so obsessed.
All right,
He really likes her shirt because she likes llamas.
Who likes llamas? Oh. Oh, they have all kinds of cute ones. Oh, I guess I can figure out the number. Hurry, hurry. 25.
You look so well. We're all messing. I do.
Okay, pick one. Everybody up there? I got 24. I thought I should have 25. We got 25 now? All right, great. I got every answer. Okay, so how do you do it? Like, how do you think about the problem? What's the first thing to do? If it's asking for the conjugate base, what is that telling you about this molecule? It's the acid, okay? What proton are you going to lose? The H. Which H? Yes, this one. So when you lose that H plus, you get this one. Okay? If you got it wrong, do you get it now? Okay. Okay, we were talking about dipole moments, okay? Remember, we're adding vectors to figure out our dipoles, and the lone pairs actually help, okay? They give more electron density on that side of the molecule. So you can see here that acetonitrile has the biggest dipole moment of 3.9. That's actually a pretty big number for dipole moment, okay? And here is this compound called acetone that I bet you've used in lab to do your dishes. Okay, everybody's using, okay, make sure you always rinse with acetone. Okay, and you put it in the waste jar, right? Okay, good job. Okay, and then there's water and ammonia. Okay, it's really important that you remember to take into account the shape. Okay, not only do you have to have polar bonds, but the shape has a lot to do with it. Okay, so here is CO2. Okay, you've probably seen CO2. It's Lewis structure before, right? And the carbon in the middle is what hybridization? Yep. This is sp. Okay. What is the O? sp2. Okay, and this one is sp2. Okay, there are polar bonds in carbon dioxide, but is carbon dioxide a polar molecule? No, because they are linear, because it's linear, and so one's pulling this way and one's pulling that way, and so your vectors are adding up to basically 0. Okay, oh, look at that, I wrote right on linear geometry. What can I say? So there's our two vectors, and they're adding up to 0. They cancel out. Okay, so if you measure the dipole moment of carbon dioxide, you get 0. 0 divide. Okay, here is methylene chloride. Have you used that in lab yet? You will. It's coming. Okay, it's a real popular solvent. That's how come you'll use it. Okay, so this is what it looks like. It's CH2Cl2, and there are 2 chlorines and 2 hydrogens attached to that carbon. Okay, well, you have 2 polar bonds, one from this carbon to this chlorine and one from this carbon to that chlorine. Okay, is that compound polar?
Yes.
Yes. Okay, because they're at an angle. Okay, they're not linear, they're at an angle. So if you're pulling this way and you're pulling this way, which way do you go? You go that way. I could feel the pull. Okay, so there's your vectors, so there's your polarity. Okay. Okay, the actual number for this one is 1.62 Debye. Don't worry about the numbers, it's just to show you how some things are more polar than others. You don't have to memorize polarity numbers. Although it's really easy to learn the ones that are 0. Just saying. All right, so this is methyl chloride is what this is called. And, or chloromethane, that's the actual name. The methyl chloride is a common name. Okay, its dipole moment is 1.87. And this is water. Water has a dipole moment of, come on, 1.85, almost the same, okay? Almost the same. Do I get the boiling points? No. Okay. The NF bond is, that's coming, is more polar than the NH bond. But NF3 has a smaller dipole moment than NH3. Explain this curious result.
Because of the shape of the molecule.
What?
Because of the shape of the molecule, it pulls in equal directions.
Okay, well, let's look at that. So here is NH3. Let's see. How about if I do it like that? And I'll draw them both the same. Okay, so notice that we have those little NH3 bonds. Okay, and then over here we have F's instead of, oops, I did it again. I'll just make this one the wedge. Okay, so nitrogen has what hybridization? SP who? SP, nope, 3. Because there's 4 sites of electron density. The lone pair counts. Okay, that's why I drew it in too. Okay, so when you're looking at the vectors, okay, we're going to have, here's our lone pair in our sp3 hybridized orbital. Which direction is that vector going to be? It's going to be going right out here. Okay, what about the NH bonds?
The hydrogens pull towards the nitrogen.
Yes, goes like this.
Is that because it's more electron negative?
Okay, who's more electronegative?
The nitrogen than the hydrogen?
Yes, than hydrogen it is, yes. Okay, what about the other molecule? We still have this, sp3, we're pulling that way, but what about those fluorines? Okay, they're pulling the opposite. Okay, so you've got your tripod pulling down and your other one pulling up. So it's a little polar, but not very much. You see the difference? Notice that here, our tripod is all pulling towards the nitrogen and up. Okay, so this is going to blast off. This one is not. Okay, that makes sense. You see how to think about it. Because that's the most important thing, is figuring out how to think. Oh, I forgot that was over there. Those are the actual numbers and the little things pulling. Okay, predict whether the compound has a large, greater than 1 is large, small, or 0 dipole moment. All right, so I'll erase those while you think so that we can read the writing. Okay. Since I forgot that was on there, I can't remember everything. Okay, so what do you think? What about that first molecule? CH3OH. What do you think? How are you going to figure it out? What do you think you should do first? Draw a molecule. Let's draw a molecule. I think that's a great start. Because when it's all smashed down like that, it's hard to see. And I'm even going to put in my lone pairs so I remember they're there. Okay? Actually, so you'll remember they're there, but you know, that's a good way to do it. Okay, so now what can you tell me about that molecule? What does it have? Does it have any polar bonds? Because if there are no polar bonds, it is nonpolar, 0. Okay, so that makes it easy. Is there polar bonds in this one? Yeah, so it isn't easy. Sorry. Okay, so what can you tell me about those polar bonds? You need to know what the hybridizations are, and you need to know the direction of the vectors. Okay, it's like vector analysis. Have you done that in physics?
Unfortunately.
Yeah. I did it too when I took it. I don't remember it anymore. I know this though. All right, so what can you tell? What are you thinking?
The hydrogens pull towards the carbon.
Okay, but these are little.
So
I wouldn't even worry about them.
the oxygen pulls.
Yeah, there's a big one. What else?
The lone pairs on the oxygen.
The lone pairs. Okay, and then what about this? Okay, so what do you think this one is? Large. Yes, and large. Large, small, or 0? I guess we're going with large. Okay, what do you think about NH4+? Okay, so let's look at that. Oh, I guess I can just write it in this one. Okay, so here is our... It's really hard to color on the smartboard. Just saying. All right, so what is the hybridization of that nitrogen in the middle? sp3. There are 4 sites of electron density. Okay, so it's sp3. So what is its geometry?
Tetrahedral.
It's tetrahedral because there are 4 hydrogens on it. Okay, so every one of them is going to do what? Cancel out. Okay. What about this last one over here? Oh, so what is it? Large, small, or 0? 0. Okay, which was your first guess, which was good. All right, what about this one now? Okay, we're going to draw it out. There's a lone pair on that nitrogen. Make yours look a little more human. Okay, so what can you tell me about the vectors in there? Look at red ones. So who's the most electronegative element in there? The nitrogen. So you have polar bonds, right? We have polar bonds here, here, and here. For the, well, it's not a polar bond, but that's where the lone pair is. Remember the lone pair poles? Okay, electron density. Okay, so what do you think that one is?
Is it small because?
It's small because some of it's going to cancel out. But yes, this one's probably small. No, it's large.
It's large?
It's large.
Is it just because it's
Because you wanted there to be a large, a small, and a zero, right?
Yes. Yes.
No, it's large. It's very similar to this one. Okay, it's large.
So it doesn't matter even though carbon and nitrogen have really similar electron negativity?
Yes, it doesn't matter. The nitrogen is still more electronegative than the carbon. The difference isn't as big as C and O. C and O is going to be bigger. Okay, so all I really want you to be able to do is look at the shape and find the polar bonds and decide if they cancel out or not. That's really the gist of the whole thing. Okay, like I say, we're not going to figure out all the numbers. Okay, so is there a problem like that in the homework? You haven't looked, okay.
I don't think so.
You don't think so? Okay. It's really hard to write them if they didn't already write them. All right, have you heard of this guy? Van der Waals. Oh, yes, no, maybe so. Okay. Van der Waals came up with this whole intermolecular forces thing. Okay. Inter-Latin scholars means between. Okay. I know you all took Latin. I took Latin. It was because the teacher was so good in high school. I went to state for Latin. I'm like, who does that? You know? I don't know. No sports for me. All right, so inter is between. So this is forces of attraction between the molecules. So why is something a liquid? Why is it a solid? Because there is attractive forces between those compounds. That's what Van der Waals forces are all about. Okay? And we're pretty much just going to talk about covalent molecules because that's what we have in organic chemistry. Okay? There is ionic. Okay? That's the strongest. Y'all know that if you try to melt sodium chloride, it's really tough to melt, right? It melts like 600 some degrees. Okay? We ain't going to be doing that. And I'm not even teaching it. Okay, so the strongest one is hydrogen bonding. Have you heard of that? It's real important. The next strongest one is dipole-dipole. And the last one is often referred to as London forces. It's induced dipole, induced dipole. So those are the three that we're going to talk about. Okay, just those three. We're not going to worry about ionic. Ionic is stronger, but if you don't have it in your molecules, we're not going to worry about it. Make a sense? Okay, have you heard of all of those? Okay, because I remember doing them when I taught your account. Okay, London dispersion forces. Those are induced dipole, induced dipole. Okay, they are the major intermolecular force of attraction in alkanes and cycloalkanes. What is an alkane? An alkane is a compound. Oh, hang on. I don't have a, because we're getting to that. An alkane is a compound that has all carbon and hydrogen and all single bonds. So here's an example of an alkane. Okay? Alkanes are all single bonds between the carbons and only carbon and hydrogen in the molecule. Okay? What do you think a cycloalkane is? What do you think? Just take a guess. Makes a circle. It's a ring. Okay? So here is the smallest cycloalkane that I can draw. It has 3 carbons in it. And I'm drawing them as Lewis structures just to make sure you're all okay. Okay. So what is, but, you know, you have, I'm trying to decide, Did you talk about hexane in lab? Did you use hexane? Was that one of your unknowns in the? Okay. Hexane has 6 carbons. Okay. It has London dispersion forces, and it's a liquid. So all those things that you used, they were all liquids, but they didn't. Why are they liquids? Okay. So what happens is the electrons in the compounds are constantly moving, and as they move, they will make little areas where there's more negative and a little bit of positive. Where's that positive coming from? It's coming from the nuclei, okay, of the atoms. So your electron cloud is kind of moving around, making little dipoles. They're induced because they're induced by the molecule that is next to it. So if the first molecule throws its electron density over to the left and the positiveness over here, what do you think the one that's next to it is going to do? It's going to do the opposite. So the electron density is going to go where that positive is. It's going to be induced by the compound that is next to it. Okay? Remember, this is the weakest force. Okay? The weakest force. All right, let's try that. Okay, so these are these temporary dipoles. And once these dipoles form, they change, molecules are moving. Okay, and what happens when you boil something? What are you doing? You're heating it up, and what's going to happen? It's going to go from the liquid state to the vapor state, right? And it's going to be pulled apart from the ones that it's next to, okay? So you are breaking these dipoles, these little temporary dipoles, okay? That's what you're breaking when you boil something, okay? Okay, boiling points increase with increasing number of carbons. Did you notice that in your distillation lab, that as the number of carbons went up, the boiling point went up? You might not have even thought about it, but it does. Okay, more atoms, more electrons, more opportunities for induced dipole, because it's just bigger. There's just more stuff there. Okay, the boiling points decrease with chain branching. So, all right, I want to show you what I mean. Less surface area, fewer points of contact. All right, so I'm going to go back because I'm going to draw you some so you can see what I'm talking about. I want to make sure I didn't write over my words again. All right, so I'm going to use the sticks. Is that okay? Going to handle it? Okay, how many carbons are up there? 7. Okay, remember every end and every bend is a carbon. Okay, so this compound is a long chain. It has 7 carbons. Okay, it does not have any chain branching. Okay, so now I'm going to draw it again. I'm going to change it up. I'm going to draw an isomer of it. Okay, now that one has a lot of branching. So that's what we mean by chain branching. Okay, now the two things have the exact same molecular weight, right? You agree? Okay, C7, whatever. All right, so now which one has the higher boiling point? Is going to be the one on the left. Okay, this one will have a higher boiling point than the one on the right. And it all comes down to the shape. Okay, so this compound is long and skinny, like a swimming noodle. Okay, if you stack swimming noodles up, what happens? The sides go right together, right? Okay, and so they have a lot of contact. Okay, this is more round because of the branching. It's more like a beach ball. What happens when you stack beach balls? Only, you have 2 balls, only part of them interact. So this molecule being so round, okay, it doesn't interact with the other molecules around it as well as this guy does. Okay, so this has a higher boiling point than this one. Does that make sense? Okay, you get the noodles and the beach ball thing? Okay. Just checking. All right, hang on. Now we're going to look at some compounds. All right. All right, so here are hexane isomers. Don't worry about the naming thing. We'll get to that. That's in chapter 3. Okay. So you'll see that this is hexane up here, 6 carbons all in a row. Notice that it has the largest boiling point, the highest one, 67.2. Okay, and over here is this compound. Can you see them? Do you have them? Do you have the whole chart on your deal? Can you see these things? I worried that they were kind of hard to see. Okay, notice how the shape of the molecules changes as you go from the left to the right. The one on the right is the most branched that you can be, and it has the lowest boiling point. Okay, they're all isomers of each other. They all have 6 carbons. They all have the same molecular weight, the same formula, just different structures. Okay, so as you increase your chain branching, okay, the boiling point goes down. Okay, so what I want you to be able to do is, like, if I gave you a list of them, put them in order. Who do you think is the most? Who do you think is next? Okay, who is the highest boiling point and who is the lowest? Okay, it's all by chain branching on these compounds. Okay, match the boiling point with the appropriate alkane. Okay, so here are the 4 alkanes that we're looking at. Okay, and here are our boiling point choices. All right, you got this on a slide, I hope. I'm pretty sure I did that. Okay, so what do you think? Anybody have any thoughts at all? What? Okay, why did you pick nonane to be higher than octane? Yep. So this one is D. And so you're picking this one to be C. Okay? I guess I could have just written the letters. All right, now what about these two? 2-methylpentane, you want that one to be B because it has a little branch, and then it's got this long chain part. It's going to be, you know, it's kind of like a noodle with a ball on the end. How's that? Okay, now that means this guy has to be A. Okay, has the lowest boiling point because of its shape. Okay, because of its shape. All right, everybody got that? Kind of nice little fun, easy thing. Okay, the next one is dipole-dipole. You must have a polar bond in the molecule, and the molecule has to have a dipole moment in order to have dipole-dipole interaction. The negative end in one molecule is attracted to the positive end in the other molecule. Okay, and they all kind of line up. This is the main force in many alkyl halides. That means, but it's the major force in lots of things, so don't just think that's the only one. Okay, so you have to have a carbon attached to a halogen. Okay, you can have 6 carbons in a halogen. That's an alkyl halide. Okay, main force in alkyl halides. So if I were to give you an example, let's go with this. Okay, and I'm going to give you the lone pairs on the chlorine so that you remember that they're there. And usually if I write them down, you write them down. Okay, so do you see the polar bond? Where's our polar bond? It's from between the The carbon and the chlorine, okay? And who gets more of the electron density? Chlorine or carbon? Chlorine. Right? It's more electronegative than carbon. Okay. So what's going to happen is there's going to be a positive side of the molecule and a negative side of the molecule. It's not ionic, it's partial. So another one of these is going to line up. The positive end is going to go where the chlorine is of the one that it's next to. Now, you see this part out here. This part out here will still do induced dipole, induced dipole. So you still get them as well. Okay? It's just not the major one. And that being the weakest one, you know, tends to get forgotten, but it is still there. All right, so here is CH3Cl, okay? And this is how they would line up, where the positive side goes where the negative is, okay? And they just kind of match up, okay? A lot of times you'll see this in your book where they take the balloons and put the plus and the minus to show the positive end of the molecule and the negative end of the molecule. Okay? Okay so far? Okay, hydrogen bonding is the king. Okay? Hydrogen bonding is the strongest of all the intermolecular forces of attraction that we will run into in organic molecules. It is only found when hydrogen is attached to an oxygen or a nitrogen or a fluorine. Okay, so if you attach a hydrogen to a fluorine, what do you have? Hydrofluoric acid, HF. That's it. Is that organic? No. Okay, so there is no other places to bond. So typically you're not going to have hydrogen bonding except in OH and NHs when those are in your organic molecule. Because you can't have an HF in an organic molecule. Does that make sense? Okay. It all has to do with the bonding rules. Okay, so this is what we're looking for. OH and NH. Okay? So, OH and NH, or oxygen and nitrogen, are highly electronegative atoms, and that bond is very polarized. Okay? I am sure that in general chemistry, you talked about this molecule. What is this molecule? Water. Okay? Do you consider water to be polar or non-polar? Polar. Okay? Does water exhibit hydrogen bonding? Yep. Okay. What is the molecular weight of water? Quick. Round numbers is good. 18. 18. What is the boiling point of water? 100. Okay, Celsius. All right, 100. That's like outrageous. Okay, the difference. Because we have other things like this compound, which is methane. What does that weigh? 12 and 4, 16. Almost the same as water, okay? But it is what at room temperature? It's a gas, okay? Why? Because water has hydrogen bonding. And when you boil water, you have to break those hydrogen bonds between the molecules. When you boil water, you still have H2O, okay? We're not doing explosive reactions where we're breaking the OH bonds. We're breaking the bonds between the molecules, which is different, okay? Now, where's the negative end of water? It's going to be where the O is. And the positive end is going to be where the, right, okay? What is it doing? I don't know. Okay. So I have these cool pictures of hydrogen bonding. Even though when I translated them to PowerPoint, they got real pixely. All right, so you have, I hope this looks better on your slide. Okay, good. So the negative end of the O is going to be attracted to the positive end on another molecule, okay, etc. And it would keep going over and over, okay? And when you have H2O, you have a compound that has two places, okay? Notice that this place up here, okay, which is CH3, CH2, that place is going to be able to do the London forces. You also have a polar bond in here besides the OH. Which bond is that? It's the CO bond, okay? So you actually have that other polar bond too. That's all going to contribute. But the major force is going to be hydrogen. Okay, okay. So this compound up here is ethanol, all right? And then I'm going to draw you another compound. Okay, that also has hydrogen bonding. I should have used the stick, shouldn't I have? This time lag is like driving me crazy. Okay, do you think this compound will have a higher boiling point than ethanol or lower? Higher. Why? It still has the same amount of hydrogen bonding as ethanol. But what else does it have?
More carbons.
It has more carbons, okay? And all this area is going to be making those induced dipoles, okay? It's like a noodle with an OH on the end, okay? That makes sense. So you should be able to go and figure out which ones are higher than others without having to worry about memorizing boiling points. Okay, we'll move on. That wasn't worth it. Okay, here's some more examples of hydrogen bonds. A lot of times they get drawn with these dots or dashed lines, okay, when we're talking about them. Notice that down here they made this compound methanol, okay, and it has an OH bond and it has an OC bond. Notice that they drew it and they made it look linear, but it is not linear. Okay, it has that bend to it because the oxygen is sp3 hybridized. Okay, here is an example with NH bonds. Okay, NH bonds. Okay, remember that compounds with OHs are called alcohols. We talked about that already. Compounds with NHs are called amines. A-M-I-N-E. Here's amine because it's amino world. I have students come back and they say, Dr. Wiseman, you've ruined me. I get all these jokes now. And I say, it's my goal. All right. I want you to tell me the compound that has London dispersion as its strongest intermolecular force. Go. Ooh, we got two already. Even if you don't know what all those functional groups are, you know which one has London as the major one. And I don't know why it's called London. All right, we're all up there? Y'all got it right? Almost. Okay. Why is it C?
It's the only one present.
Okay. What intermolecular forces does this one have?
Dipole.
Dipole, and it'll have some London. Okay. Every one of the molecules up here will have London forces. But we want to know which one is that, the strongest one. Okay. What about the next one?
Hydrogen bonding.
Hydrogen bonding. It has some dipole, and it has London. What about this one? Dipole-Dipole, and a little bit of London. But Dipole-Dipole is the strongest. Same thing down there. Okay, is that making sense? So you got to kind of look at each molecule and kind of rank them. All right, now I want you to tell me which one has hydrogen bonding with other molecules of itself. Okay. Is that freckle pie? That would involve the computer, and we are not touching it. All right, I'm going to click. You need to make a guess. If somebody's not registering, make sure yours went ... check. It should make the noise, too. If it doesn't make the music like that, it didn't work. There we go. Okay. Yep, it's B. What do you have to do hydrogen bonding? You have to have a hydrogen attached to an O. Okay, what's wrong with A? What are these three hydrogens attached to?
Carbon.
That carbon. What about these? That carbon. So that compound looks like this. Okay. Can this oxygen hydrogen bond? Yes. With water, or something like ethanol, something else that has an OH. But it cannot hydrogen bond with itself because these 6 hydrogens, they don't get to party. They're stuck with the carbon. Okay? They don't get to go to the party. And that's the thing with E also. Okay? Even though there's a nitrogen in it, that doesn't mean that it can hydrogen bond. It has to have a hydrogen attached to it. Okay? Okay, so here are 4 compounds, okay? And when you look at them, the molecular weights vary, but not hardly, okay? Like 44 and 45, I mean, it's almost the same, okay? But look at the boiling point difference, okay? So this first compound has a boiling point of minus 42. The one, when you throw a fluorine in there, it goes to minus 32. Okay, why does this compound with the fluorine boil higher than the compound that didn't have the fluorine? What does it have? Dipole-Dipole. Okay, then we go to this guy. This guy has NH2 in it. Okay, look at where his boiling point is. 17, right around room temp. Okay, room temp's around 25. Okay, so 17. Okay, why did this one jump 40 plus degrees from this one to that one? Why did it jump? Because we have hydrogen bonding between the molecules. Okay, and then here's good old ethanol. Okay, you know the rules. All right, so here's ethanol. It boils at 78. It's 60 higher than the other one. What's different? You have an OH. Oxygen is more electronegative than nitrogen. So that OH bond is more polar than the NH bond. So even though you have hydrogen bonding here, you have more of it here. It's stronger bonds because the difference in the electron density is higher. Does that make sense? Okay, now if you look down here at the little dipole moments, notice who had the highest dipole moment. The one with the fluorine did. Okay, but it did not have the highest boiling point. So dipole moment is only a piece of the puzzle. Okay, you need to look at the types of intermolecular forces, forces between the molecules. Okie dokie? Did I make you write down all those numbers? That was good for you. I didn't realize I'd done that. Okay, what about halogens? Okay, so here is this compound. Okay, with 1 chlorine, the boiling point is -24. Okay, let's go to 2, and what is the boiling point? We jump to 40. 3, we jump to 61. This is chloroform, by the way. You know what they put on the little deal and all the movies and people pass out? Okay, that's it. Chloroform right there. It's a little simple molecule. Okay, and this is good old carbon tetrachloride. Okay, why does the boiling point go up? Because what happened to intermolecular weight? It went up, right? Chlorine's 35, right? Round numbers is good, okay? So, but why didn't, okay, so we went from -20 to 40. We jumped by 60 degrees, okay? Here, we jump by 20 degrees. How come we only jump by 10, 15, 16 technically, to go on the bottom one? What changed? Yeah, the structure. Where those chlorines are located. Each one of these carbons is what hybridization? SP who? 3. SP3. Don't fall for that and say SP2. Okay. SP3. So they're all tetrahedral. So here they're all canceling each other out. But it still is bigger, so it's going to have a higher boiling point. Okay? Are we going to compare CH2Cl2 and CHBr3? All right. So rank the following compounds in order of increasing boiling point. Explain your rankings. This would be an example of a question on the test. Okay? I want you to use 1 for lowest and 5 for highest. So what do you think? Give it a go. Can you tell me which one up there, do you want to start low or do you want to start high? Sometimes it's easier to start at one end or the other. What do you feel like today? It's 11:48. We got 2 minutes to do it. Start with high? All right, who's highest? That weird thing down here. Yeah. Okay. Because why? Give me reasons. Hydrogen bonding. Now wait a minute. I see an OH up here. Ah, but that guy's very good. So this one is going to be 5. This has got the noodle with the beach ball. This one's just 2 beach balls. Okay, so who's 4? Hydrogen bonding trumps. Okay, that's from a card game. All right, you ever like where you had a trump? It trumped? Okay. All right, so who do you think is next? Okay. You'll notice that we have how many carbons here? 5. 1, 2, 3, 4, 5. And here we have 1, 2, 3, 4, 5, 6. And here we have 6. Okay, so how are you going to decide between this one and this one? You look for branching. So 3, we already did 4, is this one. Who's 2?
The branched one.
And who's the lowest? Okay. You got it? Let me see what's next. Oh, well, maybe I won't see what's next. Oh, okay. Then we're going to talk about solubility. All right, so we'll talk about solubility on Friday. We're going to knock this puppy out. Because I want you to have something to study over the weekend. Next week is our test. The only good thing about that is that you don't have lab. So you don't have to write it up. Oh, some of us? Oh.
I do lab.
You have lab?
I don't. He does.
Oh.
I have that other exam.
Next week?
Yeah.
Because we wanted, you know, we all get
Y'all are
together and have
conspiring
meetings
against
about
me.
that.
Yeah,
Yeah.
Sullivan Lake has a test next week too.
Oh my gosh, so you know what happened? We all do 4 tests, we count the days and we split it into 4. That's truly how it is. I'm sorry though. Sometimes I put ours off a week, but I was trying really hard not to do
No,
that
Smith
because
delayed
somebody
his.
else is doing lab, not me, and so. What is this? Oh, yeah, sure. Okay, run around the corner, see if Jackie's there, and she'll do it for you. Tell her I sent you.
Okay, thank you.
Hey, question. Nutmeg Lab,
Yes.
didn't we get like a lot of product?
Uh-huh.
Like a lot of product.
We
Wasn't
got a
like
fair
vial
amount.
full?
Uh-huh.
Okay. That's what I thought, because this year we all got like